In this video we're going to compare the substrates and think about the reaction conditions that favour initially E1 or E2 reactions. Primary alkyl substrates will always favour an E2 reaction, and these will occur predominantly if the base used is both strong and hindered. If the base is a good nucleophile but is not particularly sterically hindered, there is the possibility of competing SN2 reactions. Secondary alkyl substrates, which can be chiral, are apt to react by SN2 and E2 reactions. However, the use of a small strong base with a secondary alkyl substrate leads to a Zaitsev product. Conversely, the use of a bulky strong base would lead to a Hofmann product. E2 reactions will also happen with tertiary substrates. Good leaving groups and high temperatures always favour the elimination pathway. With respect to E1, this really depends on the stability of the carbocation and happens exclusively with tertiary substrates. E1 reactions don't really need a strong base, but a poor nucleophile, just like water, is going to be basic enough to remove a hydrogen atom that is on the beta carbon. E1 will always compete with an SN1 reaction pathway, and if the temperature is high, then there will be more of the elimination product obtained. Finally, the solvent rears its head again. Polar protic solvents are typically used to favour E2 and E1 reactions. This is the big picture. Let's try and break this down into substrate first, then nucleophile base, and finally solvent. Let's always assume that we're going to use a good leaving group, as this is something that is common to all four reactions, so we don't really need to muddy the waters anymore. The more sterically hindered tertiary substrate will react by a number of routes dependent on other factors, but we've got to start somewhere, right? We know that SN1, E1 and E2 are all possible reactions for this substrate, so we're always going to need to consider other layers like nucleophile or base, temperature and solvent to figure out the most likely reaction route. However, we know one thing for a fact: tertiary alkyl halides do not react by SN2 reactions. We're always going to need to think very carefully about any secondary substrate, because these will give reaction mixtures. You will definitely need to consider the other reaction conditions in order to see which reaction pathway will predominate. Not helpful, I know, but this is the reality of organic reactions. They give mixtures. As organic chemists, it's our job to try and favour reaction pathways by considering such nuances. A neopentyl group is pretty useless as a substrate. Let's think about this for a moment. This substrate is too sterically encumbered for SN2, but it's also incapable of SN1 as the primary carbocation is too unstable to form. Will this reactant undergo any E1 or E2 reaction? Pause the video and think about this. Resume when you think you have an answer. The answer is no. It will do neither, but for different reasons. Firstly, E2 is not a possibility simply because there are no beta hydrogens for any base to abstract. Secondly, E1 is not a possibility for the same reason as this substrate's inability to undergo SN1. The carbocation won't form as the energy requirement is too high and the primary carbocation is not stable. But what about regular primary alkyl halides? Well, these too will not undergo E1 or SN1 reactions. However, SN2 and E2 are both possibilities. Lastly, let us now consider the methyl halide substrate. This will only ever undergo SN2. It can't undergo E1, E2 or SN1 reactions. The next layer for determining the reaction pathway is the nucleophile and/or the base. A strong nucleophile may also be a strong Bronsted base, and this is easy to determine when one looks at the conjugate acid of that base and its pKa value. The higher this is, the stronger the Bronsted base this species will be. This will favour elimination, and particularly if a high temperature is used. Here are two different sets of reactions. They both involve a tertiary alkyl halide, but what's different here is the base or the nucleophile. Now, in the first instance, the methoxide anion is a strong base. It's also a strong nucleophile. Now let's think about its conjugate acid for a moment. So the conjugate acid of methoxide is methanol, and this has a high pKa value. So it's almost certainly going to be able to abstract a hydrogen atom via an E2 reaction. SN2 is definitely not going to happen because the substrate is so highly hindered that a backside attack just simply isn't possible. But when we look at the same substrate and treat it with methanol, methanol is a weak base because its conjugate acid would be a protonated methanol, and this has a pKa of about -2. This means then that the reaction is almost certainly going to proceed via SN1, especially seeing as this is a polar protic solvent. But again, temperature can influence this. This will happen at a low temperature, but high temperatures can still cause some E1 to occur, even with a weak base. Reaction pathways are nuanced and mixtures are possible. The image of the goldfish in the tank represents the space around a carbon atom, and the size of the fish tank represents the ease at which the beta hydrogens can be abstracted. A bulky base is not going to be able to easily abstract a hydrogen atom from a hindered substrate. Think big fish, little tank. However, the access to the beta hydrogens on a primary substrate are much easier to abstract. Think little fish, big tank. Also, the advantage of using a strong bulky base is that this minimizes any competing SN2 reaction. Strong bulky bases are good Bronsted bases, but they don't make for particularly good nucleophiles. Hence, this means that elimination reactions are easier with primary alkyl halide substrates and bulky bases. It is really hard to find a table that agrees 100% from one source to another concerning the predicted outcomes of substitution versus elimination reactions of alkyl, allylic and benzylic halides. This flowchart is simplified but is by no means prescriptive. To this end, I have included a second table in your notes. You will have to learn that mixtures of products are an inevitable outcome of organic chemistry. There is a hierarchy in this chart, and it provides a sensible rationale that should give you a satisfactory prediction in most cases. The organisation of these questions is hierarchical, and with practice, and lots of it, you'll find this becomes second nature. Let's have a look at an example of some outcomes now, when provided with the substrate, the nucleophile or base, and other reaction conditions. Always the substrate first, and this, unfortunately, is a secondary substrate. Therefore, it's possible that everything might happen. Great. Not helpful. What's the nucleophile? Well, it's chloride. We're not interested in the sodium cation. Is this a good nucleophile? It's not great, because it's not particularly polarizable. Is it a good base? No, not really. So the conjugate acid of chloride is hydrogen chloride or hydrochloric acid, and this has a pKa of -7. But be careful. Look at the solvent. DMSO is a polar aprotic solvent. Chloride would not readily hydrogen bond to this solvent, so its nucleophilicity is increased as it has shed its solvent cage. Oh, so this makes it a good nucleophile? Yes. Therefore, this reaction is most likely to proceed via SN2. What does the main product look like? Pause the video and resume when you have an answer. If this is an SN2 reaction, then we're going to expect a stereochemical inversion at the reacting center. Okay, time for another example. The first thing to do, look at the substrate. This is a primary substrate, and so our choices become narrowed to either an E2 or SN2 possibility. The iodide group is a good leaving group. Now the next thing to consider is the nucleophilicity and basicity of tert butoxide. This is a strong nucleophile and it is also a strong hindered base. And this means that this is more likely to lean towards the E2 reaction, as it's going to be more difficult to approach the carbon center. However, note that the solvent and the temperature wasn't included. So if we wanted more E2 product, is there anything we can do to the reaction conditions to bias this outcome? Pause the video and resume when you have an answer. To ensure a greater amount of E2 product, you would use a polar protic solvent, as this is going to minimize substitution, also increase the temperature. See if you can draw the elimination product that results from using this hindered base. Pause the video and resume when you have an answer. Okay, so remember, you're going to get more of the Hoffman product in this case. Time for another example. In this reaction, we first consider the substrate. Seeing as the substrate is primary, again we're limited to SN2 or E2. We have a good leaving group, so we don't have to worry about this. Next, we consider the ethoxide as a nucleophile. And the reason that we think about this as a nucleophile is because of its small and relatively unhindered size. Yes, ethoxide is also a relatively strong base, but because of its small size, the SN2 reaction is more likely. That's not to say that there won't be any E2 products, but these will feature as a minor product. See if you can draw the SN2 product of this reaction. Pause the video and resume when you have an answer. Okay, so here's the answer to that question. Please note that this would be an achiral product, as the substrate was also achiral. So the substrate is a tertiary substrate. So we are thinking here either SN1 or E1 stroke E2. Now we've got a good leaving group, which is going to definitely help the formation of a tertiary carbocation. And the next consideration isn't actually going to be whether this is a nucleophile, because we have this as a solvent. Ethanol is a polar protic solvent, and so again this is going to help the formation of the tertiary carbocation. Ethanol here is a weak base and also a weak nucleophile, and the fact that it is a weak base rules out the E2 reaction pathway. So the deciding factor here is the temperature, and heat was involved. So if heat was involved, then we're going to get less of the SN1 product and much more of the E1 product. We are going to more likely have a substituted E1 product, although there is the possibility, because there are two beta hydrogens, of a less substituted minor E1 product. See if you can draw all of the possible products from this reaction. Pause the video and resume when you are ready. Okay, so the major product, as I've said, was the more substituted E1 product, whilst the minor products include the less substituted E1 product and the SN1 product, as shown. Here we have a benzylic substrate. In fact, we have two benzylic substrates. Now the first one, with a strong nucleophile, would readily undergo SN2. However, the use of a weak nucleophile means that this reaction would take the SN1 pathway, as methanol is capable of behaving as a polar protic solvent. Also, we should notice that there are no beta hydrogens on this substrate, which would remove the possibility of any E1 reaction. But in the second example, we have the possibility of the formation of a secondary benzylic carbocation. So this would produce a mixture of SN1 and E1 products.
This concludes part C.
In this video, we're going to have a look at the synthesis of an alkene, and in so doing introduce another concept of retrosynthetic analysis, and this is something called the functional group interconversion. The target molecule that we have here is the one that we're trying to synthesize and is called styrene. Now, it's possible that you don't have to do any disconnections for this molecule, as you can change the functional group from an alkyl halide to an alkene. And this is one of the patterns that you need to get used to, is recognizing these sorts of functional group interconversions. However, there is the possibility now of placing that bromine leaving group either on carbon number 1, which gives you 1-bromo 2-phenyl ethane as your substrate, or you could put the leaving group on 1-bromo 1-phenyl ethane. And we're going to think then about the synthesis coming forward. In the first retrosynthetic route, we have placed the bromine in the primary position, and so we want to have reaction conditions that would be favourable towards an E2 reaction. So this would involve the use of a strong hindered base, high temperatures, and a polar protic solvent. All of these would minimise the competing possibilities of an SN2 reaction. The second retrosynthetic strategy places the bromine on what is a secondary allylic carbon, and here we would want to reduce any possibility of SN1 or E1 reactions. So here, if we want to have an elimination, then it's best to use a strong base, high temperature again, and a polar protic solvent.
This concludes part D.